All right, we'll get the suspense through now. Welcome everyone to IO 302, Optimizing Performance on Cloud SQL for MySQL. Thanks for your patience as we were getting started there. My name is Brett Hesterberg. I'm a product manager at Google working on Cloud SQL. I'm joined today by Stanley Fang and Ted Cho. Stanley leads our storage and database performance testing teams in Google Cloud. And for those of you who are familiar with the Linux ecosystem, Ted Cho may not need any introduction. Ted has been a long-time Linux contributor and is currently an ext4 file system maintainer. ext4 file system will show up as an important point in our discussion today. Before we jump in, we'd love to learn a little more about you. So by show of hands, how many of you out there are developers? A good chunk of the room, okay. How about DevOps engineers? A handful of DevOps engineers, great. How many DBAs do we have out there, database administrators? All right, good to see some hands going up. How many reluctant DBAs do we have out there? Oh, a few more, I'm not surprised. And do we have any managers in the audience? Oh yeah, a few brave managers here, good. Okay, a couple more questions for you. How many of you attended Google Cloud Next last year in 2017? Handful of folks. And anyone in that group attend the Cloud SQL performance talk last year at Google Cloud Next? All right, I think we've got a group of first-timers for Cloud SQL performance. Thank you all for joining us today. Let's talk a little bit about what we're going to cover. And actually, before I do that, let me just go through just a few room logistics in case you haven't been to a presentation in a movie theater. We have mics at the front of the theater here that we'll use for Q&A. If you have questions, please jot them down as we go along. We'd love to get those addressed with the last 5 to 10 minutes or so of the presentation. We also have members of the Cloud SQL engineering team in the audience. They're sitting in one of the front rows here. They'll be available, as will Stanley, Ted, and myself after the talk to answer your questions. If you get a chance and you have questions, I highly encourage that you talk with the engineers, the folks who build the product, and we'll get those addressed in one fashion or another. Okay, with that, what are we talking about today? We will start with a brief Cloud SQL introduction and then talk about how to scale it up and scale it out. From there, we'll get into a bit more deeply technical content, and you'll see as we go through the presentation today that it gets progressively more technical. We'll take a look back to last year at Next. We showed performance numbers last year for Cloud SQL, and we'll talk about how in the year that has passed, we've been able to increase Cloud SQL performance by around double. We'll talk about the tuning parameters that went into it, and then we'll talk a bit more about our future work here, which we're calling 16 kilobyte instance. It's a write optimization enhancement that's required the work of many teams at Google, and Ted will be taking us through that. I think it's a really interesting topic for us to cover as Cloud SQL because Cloud SQL first and foremost makes sure that we prioritize data integrity. And we're going to be turning off as part of, or at least talking about turning off as part of this conversation, a feature in MySQL called DoubleWrite buffer. And when you search on that term, what you'll find is that most online conversations end with a statement like, don't turn that off if you wish to maintain data integrity. We're going to be talking about doing that across our fleet and for all production instances. And I think it's going to be an interesting conversation for us to have with you today as to why we think that's safe and why we think it's the right thing to do from a performance standpoint. Okay, let's jump in, and let me first start by pointing out where Cloud SQL is in the overall Google database portfolio. Google has a fairly broad portfolio, as you can see on the slide. Looking rightmost, you see third-party or partner database offerings on Google Cloud. Google Cloud generally has a large partner ecosystem. The list you see on the rightmost side of the cloud is not comprehensive. There are many other, sorry, I have a little trouble with the slides here. There are many other partner offerings on Google Cloud. If you look leftmost on the slide, you see the in-memory databases. We just recently announced a managed Redis service. So if you have caching needs, we do have more offerings this year than we did last year, and you can expect generally the portfolio, the database portfolio, to continue to increase over time. Looking just right of center, you see the relational portion of the portfolio. It's made up of Cloud Spanner and Cloud SQL. If you haven't checked out Cloud Spanner or been to one of the talks at the conference this week, I encourage you to do so on Spanner. It's a great product to get to know. Cloud SQL's role in the portfolio is compatibility. Cloud SQL is meant to offer very standard MySQL and Postgres compatibility. We work hard to offer as close to unmanaged MySQL and Postgres as we can, so that we can say if your application works with MySQL or with Postgres, it's going to work with Cloud SQL. Most of our talk today will focus on MySQL, but we'll point out a few Postgres items as well. Okay, in addition to compatibility, Cloud SQL aims to reduce mundane database administration that's often associated with running MySQL and Postgres. And as we talk through this, I think pointing out what mundane means is important. When we talk about things that are mundane, we may have to get a little tech help up here. It looks like we've got slides that are wanting to progress as a mind of their own. When we talk about mundane, we think about simple things like telling Cloud SQL, watch how much storage I'm using, and as needed, increase the amount of storage so that I don't run out of it. We also talk about some advanced concepts that we'll get into as I look at the overall stack. Okay, we'll give it a shot here. Okay, so I think when you think about Cloud SQL, Tim Kelton from Descartes Labs does a pretty good job of summing it up. He says Cloud SQL gives his team more time to work on products or more time to work on things other than database administration that are valuable to his customers. And it's a good way to think about Cloud SQL. When I think about Cloud SQL, I tend to picture this stack. This stack shows a few different columns. Leftmost. Okay. Leftmost is a stack representing hardware. These are servers that you're racking and stacking, worrying about heating and cooling, for example. In addition to this stack, as you move right on the slide, we start to think about the operating system that must be run on the servers themselves and keeping that operating system up to date. Moving further right, we finally start to talk about databases. This is the database installation. It's software patching on the database, keeping it secure, and mandatory things like making sure we have backup scheduled so that we're protecting our data. Finally, rightmost on the slide are some of the more advanced concepts in the database world, setting up high availability or replication for scale out, making decisions about when to fail over, when is a database unhealthy, and whether we should do that automatically or manually. All of this, of course, gets tied together or plumbed together with monitoring so that we can understand how our stack is performing. When I think of Cloud SQL, I picture this stack, and I recognize that Cloud SQL's job is to turn this stack into a single API call or a few UI clicks, so that if you're a DevOps engineer or developer, with a single API call, you can spin up a very simple development database or a much more complex production database with high availability and scale out for reads. What's not shown in this diagram is one last important thing about Cloud SQL, and that is that it's backed by Cloud SQL's 24/7 SRE team. Jason from Real Massive points this out, that because Cloud SQL is backed by an SRE team whose job it is to automate and monitor to keep the fleet healthy, and then when needed, put hands on keyboards to bring up an unhealthy database, his team worries less now about databases and carrying the pager, so to speak, and more about other things in their technology stack. Hopefully that gives you a little feel for Cloud SQL. Since this is a performance talk, let's get into scaling Cloud SQL. I'm going to start with some simple infrastructure concepts, and then we'll get into some real detailed, especially MySQL level conversation. Scaling Cloud SQL up, to start with, Cloud SQL starts very small. If you're new to Cloud SQL instances start at less than $10 a month. They scale up right now to 64 CPU cores and more than 400 gigabytes of RAM. These numbers change over time. When we present again next year, these numbers will be larger. They were smaller last year, so expect more cores, more RAM, et cetera, over time. I think scaling up with respect to CPUs and RAM is pretty straightforward. What's a little less intuitive is how you scale storage performance in Cloud SQL and generally in Google Cloud. When you're thinking about scaling performance of storage in Google Cloud, note that you scale by increasing capacity. And Cloud SQL, as you see in the small screenshot here, includes a performance calculator that shows how much storage performance will be delivered to your instance based on a few factors: how many CPU cores you've selected and the capacity of storage you are allocating to Cloud SQL. What I'll note here is that as you increase capacity, we deliver more IOPS, and as you can see by the calculator, we're only delivering about half of the IOPS or so that we could for this instance based on the amount of capacity that we've selected. Last thing I'll note is that managing the mundane that I talked about earlier, where the simple checkbox here tells Cloud SQL, watch my storage capacity. If I'm getting too close to filling up my disk, grow it for me and do it on the fly. Do it without taking my database down. So I think it's a great way to point out not only how to scale up, but also some of managing the mundane. Okay, you've scaled up your Cloud SQL instance, and at some point your workload is so heavy that you're not able to continue to burden this single instance, and it's time to scale out. Cloud SQL makes scaling out easy in that, again, with a few API calls or UI clicks, you can add replication and read replicas, so that in this common configuration, we can start to send expensive read queries. Maybe we're running reports on Friday, or we're using some reporting tool. You can send those to a replica rather than pointing those at the primary instance, which is already under write load. That way the primary instance can focus on writes and reads go elsewhere onto your replicas. Just by show of hands here, how many of you are familiar with the difference between MySQL's semi-synchronous replication and MySQL's asynchronous replication? Okay, a handful of people, number didn't raise their hand, so I'll give you the 1-minute overview. Semi-synchronous replication requires that a primary instance and a standby instance, a replica, both write a transaction before that transaction is acknowledged to the application. So an application says, here's my transaction to the primary instance. The primary instance, when replicating using semi-synchronous replication, commits that transaction itself, and it waits for the replica to acknowledge that it's written the transaction to a relay log. The replica doesn't have to actually commit the transaction to data files. As long as it's written to a relay log, the replica will let the primary instance know, okay, I've got it, and the primary instance then goes back to the application and says, okay, I'm ready for your next transaction. This has, I think, 2 important characteristics. One is that in the event of a failover, we know that both our primary and standby instance have the data. We're not going to lose data on a failover. And for that reason, Cloud SQL employs it as the only way we replicate for a failover replica, the only way we replicate for high availability. The second characteristic is performance overhead, right? This is obvious. We're sending a write not only to the primary instance, but also to this secondary or standby instance, and we're waiting for both to say, okay, I've got it, before we let the application write another transaction. This differs from asynchronous replication in that in asynchronous replication, the primary instance will happily continue to take transaction after transaction without waiting for the replica to tell it, okay, I've got it as well. In this way, you can have a replica that doesn't have the very latest transactions that the primary instance has. Cloud SQL uses asynchronous replication only for read replicas. These are your scale-out read replicas. Again, for failover, we're using semi-synchronous so we can guarantee we don't lose data when we failover. We also, with a failover replica, ensure that we put it in a separate zone, a separate failure domain, if you will, within a region, so that we have higher fault tolerance. With a read replica or for read scale out where we're using asynchronous, we let you put those anywhere you want, and again, we don't use them for failover. So what you see in this diagram is a very common configuration. I have a high availability configuration. I have semi-synchronous replication between my primary instance and my failover replica. And I've also added an asynchronous read replica for read scale out. So I'm moving read load off of my primary instance so that it can focus on write load. And this is what we're talking about when we talk about Cloud SQL scaling out. Now, an important note here is that while Cloud SQL makes all of this an API call and makes scaling up and scaling out easy, it doesn't tell you when to scale. And that's important because it still requires you to know your database numbers. What you see in this screenshot is Cloud SQL showing you a basic set of metrics in the Cloud Console. In addition to those metrics, we in Cloud SQL enable the InnoDB metrics table. I encourage you to get to know that table. It contains a wealth of performance information about MySQL and will help you make decisions about when to scale up and when to eventually scale out. With that in mind, let's take a look back, and I'll ask Stanley to take us back to next 2017.
All right.
And talk to us about what's changed since then. Let me actually take that back from you.
And slide first, yeah.
If we have trouble with the advancing, we'll move it back over here.
Okay.
We're getting interference from another clicker somewhere. So if we can stick with the space bar.
Okay.
Okay.
I'll advance your slides for you.
I can do that. All right. Okay, so let's take a look at the Cloud SQL performance. We don't need the pointer though. Well, it's okay. I'll just wave my hands there. So, so let's take a look at the Cloud SQL performance in 2017. What's shown here is a typical Sysbench OLTP run. What we run is a step load kind of test, with each step doubling the load of the previous step. We started with 1 test thread, and then 2, then 4, then 8, and then all the way to 512. What's plotted here is TPS, transaction per second, and each step runs for about 20 minutes, and for every second of those 20 minutes, we collect the TPS data and then plot it here. So this is, you're gonna see a number of this kind of graph throughout the presentation. This is our standard way of benchmarking and plotting results. The benefit of this is you will be able to see a lot of variability throughout this 20 minutes run, because every second of the data is displayed on this chart. So what you see here is the red line is our performance in February 2017, and the green line is the performance in August 2017. And there are 2 main reasons for this kind of improvement. One is we did some level of database, and especially InnoDB tuning, to stabilize the performance of database and to allow the underlying storage performance improvement to show up at the database layer. The second fundamental reason for this kind of improvement is because our persistent disk has made a lot of performance improvements in both latency and throughput. Remember that Cloud SQL is built on top of Google Cloud Platform and uses persistent disk as an underlying storage foundation. Next slide. And you can see similar graph for the Cloud SQL Postgres performance, and this one is for Postgres HA. And the blue line is February 2017, and the green line is November 2017. And for similar reason, we are seeing about 2x improvement in our end performance. So then you might wonder, what about 2018 and these data for 2017, 1 year ago, and what about now? And actually, I encourage you guys to find out by yourself. Please feel free to take pictures of this slide because there's some information here. So one tool I really want to bring up to your attention is a tool called PerfKit Benchmarker. And so basically, we decided to open source all of our benchmarking code, not just database, but also compute, storage, and everything into a tool called PerfKit Benchmarker, and it's available on GitHub. For the database-related one, it's called managed relational DB.py. That would be the starting point. And the fundamental reason we want to open source our benchmarking tool is to be purely open and transparent. So you get to see exactly what we are benchmarking as. You get to read the code, you get to see how we set up the framework, you get to see what kind of parameters we pass into the tools, you get to see what kind of tools we use. And we actually call into Sysbench and PGBench when doing this kind of benchmarking. So the other benefit of using PerfKit Benchmarker is you can use exactly the same tool and the same methodology on other providers and find out the numbers by yourself and make your judgment. So our canonical test configuration, when you decide to try the PerfKit Benchmarker, our canonical test configuration is basically we always try to make sure the data set is large, so it's 5x RAM, and we use N1 standard 16, and we always try to fully provision the underlying storage, which it should be 1.7 terabytes for PDSSD and for the best performance possible. And then we place the test client in the same zone as the database, and we run each load step for long enough so we get to observe the variability. So next slide. And then besides the benchmarking tools and we open sourced, we also published our tuning parameters. Again, please feel free to take pictures here, and there's a tiny URL to the lower right part of the presentation. And it shows the number of InnoDB flags we tuned to achieve the effect on the left-hand side. As you can see, the performance effect of the left-hand side is more stable, more consistent than the right-hand side. And the documentation also describes and explains the justifications and reasons for why we tune each of those flags. So next slide. Now, looking ahead, what is next? So today we're going to spend quite a bit of our time in this presentation talking about a problem we want to tackle. We have tried to tackle in the last few months or quarters. Actually, the problem is about scaling writes at a very high concurrency load. Now, high concurrency, high is always in the context of some definition. So here we target sysbench concurrency test thread at 512. So what's shown here is an 8-hour-long run of sysbench OLTP at 512 threads. As you can see, the database performance varies by at least 3x. It can go as high as about 3,000 and drops down to 1,100 for the first half of the test, and then for the second half of the test, it drops down to about a couple of hundred, like 100 to 200 from time to time. So with this kind of variability in database, for many developers, the database will be deemed like essentially useless because, first of all, it's hard to do capacity planning with this kind of performance. And second is that for those deep dips of TPS during the second half of the test, and it easily can translate into timeouts from the application server. So basically, a performance problem would turn into availability problem. And the third one is, if a database is an important piece of a critical user journey or user experience, for example, populating some of the fields on the UI or saving some temporary states as user going through a set of dialog or UIs to complete something end-to-end, then this kind of performance will lead to pretty bad overall user experience for the application. So then let's take a look why that problem happens. Where exactly is the problem? So what's plotted here is what we call InnoDB flash lag. So for those of you who have read into the InnoDB and the ways InnoDB handles writes, basically each writes when InnoDB processes a write, and it writes the transaction to the redo log. And that's as soon as the transaction is committed to the redo log, the transaction will be considered successful. Meanwhile, the data page in memory will also be modified. But the data page will be flushed asynchronously as a backend to the data file. Now, what's plotted here is called a flash lag. That is the difference in bytes between the latest write that has been successfully committed to the redo log minus the oldest write that is in memory that still has not been flushed to data file yet. The flash lag is generally equals to the size of the redo log. Now, in general, most of the database, almost all database, especially MySQL, has a limit on the size of the redo log because if the redo log is too large, it will affect your crash recovery time. So when InnoDB sees the flash lag or the size of the redo log grows approaching that limit, by default it's at around 80 to 82% of that limit, then which is plotted as a red line, horizontal red line on this chart. That is when InnoDB will go into what they call a sync flush state. What a sync flush state means that is when the flash lag or the redo log size is at, in this case, 820 megabyte. Then when the next mutation comes in, InnoDB will not process that mutation, but instead it will go into its in-memory dirty pages, find out the oldest dirty pages to flush, successfully flush and writes that data page into the data file first, reclaims the corresponding space in redo log, then it will take that new mutation. So this forms a stop and go pattern in the end TPS graph as we see. And this is the fundamental reason why you're seeing this kind of performance variability. That, going to the next slide, is we're going to see how we're going to control the flash lag. So as you can see, flash lag is how much lag the dirty page flash is behind the incoming mutation rate. So logically, it seems very simple. If you want to control flash lag, you just want to make sure that database can flush dirty pages at a rate that is higher than incoming write rate. So there are two angles to tackle this problem. One is if you stop incoming writes, you have 0 writes, then you will not have flash lag. But that's not acceptable. We want to make sure that our instance can support as higher incoming write rate as possible. So the next angle to attack this is to make sure the database can flush dirty page as fast as possible. So there's a concept called InnoDB DoubleWrite. Obviously, if you disable DoubleWrite, you basically cut the write load during dirty page by half, essentially doubling the rate the database can flush the dirty pages. Now we're going to talk more about what is InnoDB DoubleWrite in the next slide. So for those of you who have never heard of InnoDB DoubleWrite, this is a quick refresh. It's basically InnoDB DoubleWrite does exactly what its name says. double write twice. So when InnoDB wants to flush a dirty page, it writes each dirty page twice sequentially. First to the double write buffer, then to the actual place in data file. Then why? Why does it do that? Why does it have to do that? So it has to deal with a concept called torn writes. Torn write is that a on-disk data page that is partly new and partly old. It happens when the write operation of a 16 KB data page was interrupted in the middle of the write for any reason. Then when the torn write happens, then the only way to recover from torn write is to take that backup data page from the double write buffer and use that to recover torn write. You cannot use redo log to recover torn write, a torn page, because to replay redo log, you have to have the original old page in its correct form to replay the redo log. But with the torn page, you have a page that is some part new, some part old, that you simply cannot recover unless you have a backup copy of that page, which is why InnoDB has to do double write. So then the next question go deeper, a little bit step deeper, is how could a torn write happen? There are two major reasons for torn write to happen. One is a disk. So any traditional disks generally do not have atomic writes, and they can write at 512 byte sector size. Many disks have 4 KB physical block size. Even if they support atomic writes, that would be at 4 KB boundary. And for a 16 KB data page, that means that if it's anything that fails during the 16 KB data page write, only part of that might be written to the disk. That's the first reason. Second reason is the file system. Now, let's say you have physical disks that you buy special hardware that can support 16 KB atomic writes. The file system still has to do some magic to make sure that the writes are sent to disk at 16 KB aligned boundary. So in general, most of the file system ext4 those, they have 4 KB as a data page size, and even the Linux kernel has 4 KB as page size. That means files are only guaranteed to align at 4 KB boundaries. Now, if a file that is aligned only at 4 KB boundary but is not aligned at 16 KB boundary, then a 16 KB write into that file may actually span 2 physical blocks on disk, which is going to break atomicity again. So, next slide. The solution we come up with to tackle this problem to allow us to safely disable InnoDB DoubleWrite is to try to achieve 16 KB atomic writes in our storage stack from top to the bottom, end to end. So first, I'm going to introduce these layers from bottom to the top, actually. The first of all, we have worked with very closely with the persistent disk team to create a 16 KB physical block size PD that will provide physical block level write atomicity. So I want to call out this because this is very unique and special in GCP, that there are some prior arts in the industry. You will have to purchase special hardware. But with GCP, all you have to do is to press the up arrow of your keyboard, which I suppose you have typed in gcloud before, and then add a new parameter called physical block size equal to 16 KB. Enter. You have a special disk that supports 16 KB atomic writes. So the next layer of the stack that we worked on, which Ted will talk a lot more in detail, is we configured and used a new innovative feature in ext4 called BigAlloc. With BigAlloc, we forced file system to allocate and align files at 16 KB boundary. And the third one is that to ensure that the Linux kernel block layer file system do not split writes into 16 KB boundary, we worked with our container optimized OS team to introduce extensive regression and qualification tests, and to ensure that when upstream changes the kernel code, we catch those invariants that were broken, and we make sure that the OS itself does not break write. The fourth one that we actually also worked with GCE virtualization teams to make sure some of the critical parameters in VirtIO layers are configured properly. Mainly it's max segment size and max sectors KB, and they have to meet certain invariants for the kernel to not split writes into 16 KB boundary. The last one at the top level is that we have to configure InnoDB to use ODirect. So with that, I would like to invite Ted onto stage to talk about container optimizer. Oh, sorry, there's too much slides here. So I want to show the effect of disabling double writes. As you can see, if you recall the flash lag graph in the previously, it was hitting the red line consistently. This is with the 16 KB feature. As you can see, we are able to effectively suppress the flash lag well below the red line. And the next slide shows the TPS result. And showing here on the middle of the chart is the TPS running exactly the same load, 8-hour run, 512 threads, and the performance is generally pretty stable and consistent. And the lower right corner was doing 4 KB and double write. So, sorry, here.
All right, so before I start, is my mic on? Excellent. So before we continue the story of how we're able to enable the 16K instance feature, I want to take a brief detour and talk a little bit about container optimized OS. Some of you may have heard about container optimized OS, also known as COS, because it's the preferred recommended image for Google Kubernetes engine. It's basically a stripped down Linux operating system that has a security hardened kernel, verified boot, and since it's stripped down, it has just the software you need so we can minimize its attack surface. Since it's based on the open source Chromium OS, we have a very rapid release cycle, and that's important for two reasons. The first is we can get security fixes out and into COS very rapidly. And the second is it will also allow us to get new features, new innovations deployed very rapidly. And not only is it the recommended image for Kubernetes engine, we also use it as the basis for Cloud SQL's virtual machines. And so that's how we actually deployed the kernel changes and some of the user space changes we needed to support this particular feature. So just to review, what are the two, there are two kernel guarantees that we have to be able to make in order to make sure that 16K database pages don't get partially written to the disk in the case of some kind of instance failure or hardware failure. And the first is that we need to make sure that the database files are laid out in logical chunks that are 16 kilobytes, what we call clusters, and I'll talk more about that on the next slide. And then the second thing we need to make sure is that these I/O requests don't get broken up into multiple requests, since that might lead to a torn write in a failure scenario. So to accomplish the first thing, we used a file system feature called BigAlloc. It was originally developed to optimize write patterns for large-scale cluster file systems, such as Google's GFS. And what it does is it works around a restriction in the Linux virtual machine, which does not allow the file system block size to be larger than the page size, which on Intel x86 architectures is only 4K. And so therefore we can't make the block size larger than 4K. So what we do instead is we introduce a new concept called clusters. And clusters are composed of a power of 2 number of 4K blocks, and data files get allocated in units of clusters. We still send the writes out in 4K blocks, but the file system tracks them in 16K clusters. And this feature has been around for quite a while. It actually hit the mainline Linux kernel in 2011. But it was only had been used for very restricted use cases. As I said, the original use case of this was for large-scale cluster file systems. And so when we looked at what we would need to do in order to enable this feature for use in Cloud SQL, there were two things that we decided we had to do to make it be production ready. The first is that we had to add support for online resizing. This is so as your database grows and you have a need to store more data, Cloud SQL will make a request to the persistent disk to grow the size of the persistent disk, and we need to be able to grow the file system to use that extra space for the expanded persistent disk. And then the second thing we needed to do is we had to add extensive regression testing to make sure that all of the new corner cases that Cloud SQL might use were actually exercised in our regression testing in the COS kernel to make sure that there weren't any problems. Because even though this BigAlloc feature has been around for a long time, it's not a very commonly used feature, and so there was the possibility that there were corner cases that no one had noticed might not have been working quite right. So for the second requirement of what we needed to do, we had to audit the Linux IO stack. Historically, all operating systems, including Linux, will merge adjacent requests in order to make things more efficient, and then if there are limitations in either the SCSI controller or the actual SCSI disk, it might break requests in two in order to deal with those limitations. And we had to make sure that each layer in the IO stack, starting at the file system layer, to the Linux block layer, to the Linux SCSI layer, to the VirtIO SCSI driver, all did not do what they're allowed to do historically, which is to break requests up, to make sure that if they did, they only broke them at 16K boundaries. And so that required doing an extensive audit of all of those code paths. And after we did that, we had to ask ourselves the question, so what if future Linux kernels might make changes in the storage stack and all that auditing work might no longer be valid for some new upstream kernel? And so what we did is we added additional regression tests that actually tested to make sure that writes would never get broken up at inconvenient boundaries. And we added that to our continuous testing regime that we use as part of our build and release process for the kernels for container optimized OS. And that's to make sure that this guarantee that we've made after auditing the code will continue to be true in future Linux kernels. And so the final point I want to make here is that this effort required collaboration across a large number of teams at Google. The Cloud SQL team, the Container Optimized OS team, the Persistent Disk team, and the GCE virtualization team. We all work together in order to make this feature possible. And it's sort of a testimony to the sort of things we can do when we take really good people working at multiple layers across the product to produce a feature like this. Okay, and back to Brett.
That's a great point, Ted. So to summarize a little bit and talk about next steps, we'll wrap up here with just a few points. When you think about scaling Cloud SQL, start simple. As I mentioned, scaling up is intuitive, except perhaps that scaling storage is aligned with scaling its capacity. So note that capacity and performance have a relationship in Google Cloud generally and in Cloud SQL. Look forward, of course, to larger instance types and continued storage performance improvements. All the numbers on the slides that we showed hopefully will be outdated in some number of months. The commitment that Cloud SQL has, in addition to being compatible, which I mentioned is your application just works with Cloud SQL. Additionally, we also are committed to being open. And I think that shows up in a few ways. Stanley mentioned that our perfkit benchmarker is fully open source. You see the tiny URL there. We host it on GitHub. We encourage you to run it yourself. It should help you set up a test environment. It should allow you to compare Cloud SQL against other database services or a database that you're running yourself. And it allows you, because it's open source, to change the test parameters, make them look more like your workloads. The other thing that Stanley pointed out is when we tune a database, we tune it not only for ourselves, but hopefully we tune it for everyone. And we've posted for the past couple of years our tuning parameters as Cloud SQL on the third bullet point you see on the slide, which is the bottom URL. I encourage you, if you're not running Cloud SQL on GCP, to start with our tuning parameters. If you're going to run MySQL of your own accord, maybe on a compute engine VM, and then continue tuning from there. Our parameters will give you better performance than a default MySQL installation will on compute engine, and we think it's a great starting point, if nothing else, for you. Ted talked about what it took to align teams within Google so that we can safely turn off DoubleWrite buffer and produce what we've called 16 KB instances. If you have interest in seeing those for yourself in Cloud SQL, please send an email to this email address. We have started an active alpha program. You're more than welcome to join to see how write optimization may benefit your workload. What you'll also see from the Google teams is that we'll make these options available to you if you're choosing to run MySQL outside of Cloud SQL as well. So if you're using container optimized OS, and as Stanley mentioned, you can configure persistent disk with 16 kilobyte block size, you'll be able to benefit from this yourself as long as you stay within some of the parameters. As you can see, there was a lot of work from Linux kernel down through the storage stack to make sure this is safe, but we're going to do our best to make this open like the rest of Cloud SQL to you as well. I want to point out a couple presentation picks. We're on the really kind of the first major day of the conference. I'm going to give you two shameless plugs to start out. First, we have a best practices for migrating to Cloud SQL session tomorrow afternoon. If you're interested in migrating a workload to Cloud SQL, stop by and take a look at this session. It'll talk about how to do that, especially to MySQL with low downtime. Just later this afternoon, we're doing an introduction to Cloud SQL and Kubernetes. If you'd like to learn more about Kubernetes and how it can work with Cloud SQL, take a look at this session, which is just after today's session here. And last on the list is IO 225, which is what's new with Spanner. If you haven't been introduced to Spanner, I think this is a good session to pick up what's new, and it'll of course give a bit of a product overview on Spanner as well. With that, on behalf of Stanley and Ted, I want to thank you for spending the last 42 minutes with us and for bearing with a few slide hiccups along the way. We'd love to open things up to your questions, and if we run out of time for questions, we'll ask that some of our Cloud SQL folks stay toward the front of the room so that you can catch up with us after the session. Thank you, everyone.